All righty, the recording has started. It's October 21st, 2024, and this is the Western Automation Monday morning technical training class with Blake Timmons and Dan Roth from Lovato. Blake is going to give us a presentation on electric circuit control and protection. Blake, thank you very much, and the floor is yours.
All right, thank you, Pierce. Let me get this first slide in here. And what we're going to talk about, like I said, is motor controls, some control components, and some power distribution and safety. Now, this is a very basic presentation, and it's really intended to just introduce the terms and just some things that you need to be aware of as you're speccing out or selecting products in each one of these. So with that said, I always like to start with the motor starter. What it consists of. A lot of people don't realize what a motor starter does. We're passing part numbers back and forth a lot, and they don't realize that all it is an electromagnetic switch. But you got three things you're switching, one for each leg of a three-phase system. So as you can see here, as I got in the drawing, in the middle here, you got your line coming in, and you can see the three switches. And you can see off to the left the coil that switches those things in. And it's just typical that when you get one of these contactors, you're going to see an A1 and an A2 on there. And that's pretty much every contactor I've ever seen is going to be for the coil, the A1 and the A2. So keep that in mind. Now, also, in addition to the contactor, you'll have some internal auxiliary contacts. All right, and you'll see here, I've got a picture of a normally closed one, and I got a picture of a normally open one. That's pretty much, you can have either or both on those contactors. Now, when you look at our contactor over here to the left, I've tried to identify some of these terminals. There you are, you can see the coil kind of down in there in the back, and that's your A1 and A2 terminal. We also feed the bottom, so we have an A1 and A2 terminal down there also. Then you can see with the blue line, the auxiliary contacts that come over to the side. Okay, so that said, let's drill in a little deeper how a contactor works. Okay, so the first thing you're going to do is you're going to land your motor leads and your power leads coming in. Okay, and then you're going to have the coil. We say coil here in Texas. Okay, coil. So you'll have that. And when you energize that coil, you'll energize the magnet around the armature. There's a little armature that works back and forth in there. And when you do that, it'll close those contacts and apply power out. Okay. And then as you remove that coil, that circuit, then it'll drop out the magnetic coil and it'll de-energize. And of course, you'll get a little bit of an arc, and then you'll lose power to the motor side. Well, that's pretty much how you control a motor. You turn this control circuit off and on. And a lot of times, or almost every time, you'll run it through a set of overloads. So when that overload sees too much current, you'll turn the motor off right here at the coil. Look at that. So here's a contactor for a reversing contactor I did. This is very common. So to reverse the direction of a motor, you have to change any two wires in that three-phase circuit. And you can see as I come in here, I feed on the right side over here, I feed the line side, the top side of two different contactors. But on the bottom, you can see where it switches those two. Let's get a little animation here. You can kind of see what I'm talking about. You apply the voltage. Okay, as soon as you apply the voltage, you'll start the motor turning. And then you want to turn it the other direction, but you can't because it's mechanically interlocked. You do not want both of those coming on at the same time. So we mechanically, not only electrically, but we mechanically interlock these. So once you get it turned off, then you can switch it to the other side and turn it on. That's how a reversing contactor works. Okay. Now, you'll see that little purple box down there. I kind of left it blank right now because that's where your motor overloads are going to go. Here we go. Now I'm telling you how to separate mechanical interlock. And we do. This is a terminology that's used a lot for something A full voltage reversing contactor. That's FVR. When you see that on a quote or request, that's what they're talking about. Okay. And then there's your motor overloads I talked about. That's a symbol for the heaters, thermals. Okay. You also have a changeover contact. Works a little different, but you don't really reverse the lead. You just have two different sources coming in. You see how it works? Yeah. There it is. Turn it over. You don't swap the leads. Mechanical interlock. Good. Now let's talk about the overload protection. That purple box we had at the bottom. So that goes typically right in the bottom of the contactor. A lot of them are a direct mount. We do have some independent mounts for those things, but most of them are going to be a direct mount right into the contactor. Okay. It's designed to protect the motor. Okay. A lot of people say, well, with this 10 amps I got on the overload, will that handle the motor? I said, yes, because these are what they call class 10 overloads. Takes 10 seconds at that rated current before it'll trip. So it handles the inrush of the motor. Okay. Different types. You have some bimetal ones, and then you also have some electronic ones. So in the bimetal ones, they have the built-in thermal where it'll hold up to 10 seconds before it trips. But in these electronic classes, you got a little more control on this thing. You can do a real quick trip for some semiconductor devices you may not want to destroy. So you'll do a class 5. But you can see with electronic, we go up 10, 20, 30 seconds before it'll actually trip. A lot more control on an electronic. Actually, you're going to pay a little more for electronic overload. Here's my animation on the overload tricking. Okay, so you have your motor, your line side coming in from the contactor, and you're feeding out to the motor. Okay, you have that control circuit that'll go up to the coil on the contactor. All right, you have a motor overload. Excess heat happens, right? Heat and current are detected by the overload. Boom, little arc. Yeah, that's when we turn it off. It trips. So it turns off the control circuit to the coil of the contactor. So the contactor drops out. So the only real switching you get in an overload is just that little control circuit. And it controls the switching of the contactor, which is made for the heavy duty switching. Okay. And it turns off. All right. Now, when we talk about motors, we do want to, I wasn't sure what motor brand y'all handled. I didn't want to offend anybody, so block that out a little bit. But when you look at motors, you got people always ask them, I said, well, what's the amperage you're looking at? Always go to the running amps or the full load amps. When we size things, we go by amps. I'm not always concerned what the voltage is, but I do want to know what amps. A lot of times people, I'll ask them, well, what's the voltage of the motor? And they'll give me this 208-230-460. Okay, and a lot of our stuff, we need to know which one is it? Is it 208? Is it 230? Is it 460? Some companies have dual ranges on their contactors, but we don't. We because you see the big amp difference in there. If it's 460, you're half the amperage, so you're going to use a lot smaller contactor. Okay, those are just some of the things we look for in a motor. And you also have to realize when you're dealing with motors or you're dealing with current for the contactors, you got to know what category it is. And a lot of times, most every time our contactors are sized for the AC3 category. These are right out of, you can Wikipedia, you can do current categorizations, and you'll see these AC categories, okay, for AC motors. And AC3 is typical. It's a squirrel cage motor for starting and stopping. But sometimes you'll get an AC1 rating. Sometimes people will only use these contactors for resistive loads, for heating elements, and maybe some incandescent lights. All right. So there's these different current categories you got to be aware of. Okay. different contactors for different applications. As I mentioned earlier, we have our reversing and changeover contactors. It's a double thing with a mechanical interlock in between. We have definite purpose contactors. This is the one that gets people a lot. A definite purpose contactor, all it is a contactor that's certified for definite purpose. What is definite purpose? What do you mean? Well, most of our contactors, they're going to be sized for 2 million cycles. The industrial world, we need a lot of cycles. We need them to go a long time. But sometimes you're doing these things for your home unit, your AC unit at the house. And we can derate these things by calling it a definite purpose contactor. And you'll see that I can take what would be normally a 9 amp contactor for a motor. I can almost get 20 something amps out of it because you promise it's definite purpose. And you're only going to use this for 250,000 cycles, not more. So that's how we're able to derate it. We have some other ones that are for capacitive switching. And that little adder block on the front of it, that's a resistor contact, a set of auxiliary contacts with a resistor in it. So when you go to pull that in, it's got an early make contact on it. So when you go to pull that in, to pull in a capacitor bank, you're going to bleed off some of that surge. We've all seen that arc when a capacitor shorts. You want to bleed that off a little bit, and then you can close your contactor. Makes them last longer. That's a little kit on ours that you can put in the front of it. And then we have some other contactors, and you'll see in the back of our catalog, all these different lighting categories. Back to those AC categories I mentioned earlier. What kind of current are you using? Now you have them for tungsten, ballast switching, dynamic braking. That's you're doing with a VFD. That's going to be some DC current, which you got to break. A lot of those poles have to be wired in series. Okay, and DC switching, kind of the same thing.
Hey, Blake, the
Yeah.
capacitive switching product, that's very interesting. There's one of those in every standard voltage source VFD. Is that
Yeah.
does Lovato supply those to the VFD manufacturers?
I don't know that we do. I don't know that we do that I'm aware of. They do a lot of stuff they don't always tell me. So they
Yeah,
might.
it'd be an
Yeah.
OEM thing, but that's exactly what you do to slow charge the cap bank on a standard VFD.
Yeah.
You bring resistors in first for a few milliseconds, and then you short them out with a main contactor.
Yeah. Yeah. Good. Okay, what's next is now our motor protection circuit breakers, manual motor protectors, MPCBs. That's all these terminologies are used. I've seen people get kind of loose with that and use a lot of other stuff, but manual motor protectors is the main thing I see a lot of there. And it basically the same kind of deal. You can you'll run you don't have any remote control off of it. But what you can do is run your motor leads into the top. I mean, your supply leads into the top of it, and your motor leads out the bottom. And you can manually turn that knob, that rotary switch, off and on. And so you've got a little bit of a disconnecting means there. And you also, if you'll look up just to the left of that big dial, you'll see a current adjustment. So you also got a thermal overload built in. It's got a disconnect, manual off and on. And it protects it. It's got a higher short circuit rating also. So a lot of times you can replace your fuses, your motor fuses feeding the motor. Ours will also detect phase loss. So if you get a single phase situation, it'll trip out for you. There's a handle and it'll lock. You got a little bit of a lock on there. And naturally, it's not going to be a real secure lock. I mean, it's kind of delicate right there. It's just enough to indicate to somebody else, hey, don't turn this on. I may be working on it. You have a test function on it. So you can trip that button to test it to see if it's going to trip for you. You have the current setting I mentioned and a little magnetic trip indicator. So you just kind of look at it and see if it's tripped. Now, here's some of the advantages of using the manual motor protector. As I mentioned earlier, you can look over here to the left. Just for a local stop start, I have at the top. But at the left, you can see you have a fuse, and then you have a motor overload protection, and then you got a disconnect. Well, I've just replaced those three items with one item. So naturally, it's going to save you some labor. May even save you a little money time you add all that stuff up. Let's look at the right side over here. This kind of uses a remote start stop. So naturally, we're going to have to put a contactor in there to get some remote control on it. But where I would have before used a fuse, a contactor, a motor overload, and a disconnect, now I can just use a contactor and one of these motor protectors. And they can be close coupled. You don't have to wire between them. We have these little bridging things you close couple them. Big advantage in the panel building business using these things. And your motor protectors, we do have quite a wide adjustment range on them. Braking capacity is 50 kA, UL type E and F. I don't know if you guys get into that. If you don't, usually these 508 shops do. Type E means you can kind of use it for a service entrance. You don't have to have a big disconnect ahead of it. Type F is kind of a condition that if you get a short circuit, that you can still reuse it. So basically, if it blows up, you can still use it. Thermal magnetic protection, automatic trip indicators, it works. Save time, save space, save money. Okay, now we go into a soft starter. What is a soft starter? I get a lot of people trying to buy soft starters and VFDs and not really sure which way to use it. But basically, a soft starter is a device used to just ramp up and ramp down a motor. All you're trying to do is cushion the mechanical load on it and kind of shave off that peak demand when you get a big surge. You're trying to shave that off a little bit. Okay. Here's a diagram of how that works. So you have a starting voltage on a soft starter, and then you're going to ramp. Okay. And you can determine where that starting voltage is typically and how long the ramp is. See if I got an animation on that. Reduces voltage drops in the networks, minimizes starting circuit, 4 starts per hour doing that. It reduces the peak demand. Minimizes the maintenance. Yeah. So here's a little discussion we get on the different types of soft starters. Sometimes you'll get these soft starters and they'll have 3 SCRs in them, 3 big transistors in them. That's what you're looking at over here on the left. I mean, on the right side, the other left. You'll see you have these SCRs. They're basically triacs, back to back. SCRs are triac, and you'll use that to ramp up your motor. Well, some of them years ago they decided, we really only need 2 of these things, which you'll see on the left. We can just feed that middle one straight through. And that'll take care of the ramping. We could save some money. We can on cost of building these things. We can save a little bit of size. So the industry went to a lot of these 2 SCR soft starters years ago. And the diagram here they're trying to show you is on a high torque starting load, 3 SCRs are really what you want to be. A lot of these fans and mixers that just spin real easy, you can use that for the 2-phase control. But when you get into these big, heavy inertia grinders and stuff that got to start off under a load, yeah, you really need these 3 SCR type, 3 controlled outputs, I think we call them. Let's see here. Here's some more talking about the load current. The how it ramp up and then it tapers down. Let's see, 2-phase, more of that, 2 or 3-phase control. So you get less heating with the 2 phases, low cost. I mentioned that. And here's just a little animation of how they work. So what happens is you'll supply your voltage, and inside almost all these soft starters now have a little bypass contactor built in them. Okay. Well, used to we'd ask, does that have a bypass in it? Well, why do you want a bypass? Is because after you've done all the ramping, this thing doesn't need to sit here and run through the SCRs. You can run it through a little bypass contactor, and it can be a little smaller because you don't have that inrush current. So let's look here. What happens if we give it initial voltage? We ramp. When we get to the top of the ramp, the contactor pulls in and it relieves the SCRs of all the load. Same thing on the de-energize. First thing I'll do is de-energize that bypass contactor, and then I'll do the ramp down sequence in reverse. Here's another term that comes up when people start talking about bypass, and you're bidding these jobs and got some big projects, and people say, well, I want to bypass on my soft starter. Like, what do you mean? Because soft starters come with a bypass. You talking about a service bypass? That's what this does. So if somebody had a real critical application and that soft starter went bad, they want to be able to turn a contactor on over here and bypass it. So now you have what we call a service bypass. And these come in different flavors. That's a one contactor bypass. You can do a two contactor bypass. Okay. You can do a three contactor bypass. So you can by having a three contactor bypass, you can just totally isolate this circuit here where the soft starter was. You can work on it while you're doing the other, while you got it in bypass. Just a little terminology to be aware of. VFDs, I'm not going to get too deep into VFDs. That's pretty much a class on its own. But I just want to say that the main purpose of a VFD is to control the speed or the torque of a motor, not just for starting it up. Really, VFD is a better control of things if you need that. Soft starters work good just to help reduce the mechanical shock and the peak surge on the voltage. But the VFD gives you a lot of control, and it has different names. People call it variable frequency drive. Guys in Europe always call it a variable speed drive or ASD, adjustable speed drive, just different names, just variable speed. Okay. And you can see in a drive, you just have all these different functions and ways to program it, do all this control with it. And then you have a lot more protection out of it. Soft starter, yeah, I can get some single phase detection out of it. I can get some overcurrent detection of it, but all these braking and resistor overload, overspeed, you just get so much more out of a drive. And the software that comes with the drive, so you usually got a lot more analysis with it. There's some applications, typical applications where you'll see them side by side in a panel for the fans and the conveyor belts and stuff, pumps. Let's talk about control relays now a little bit. Control relay works a lot like a motor contact. You still have that little electric magnet in there, and you're triggering a set of contacts. You're going to turn something off and on. And it's good for isolation. They have different voltages like the contactor. You can power them with 24 volts DC, 24 volts AC, 110 volts, 48 volts, 480 volts. You just got to look. When you look at a relay, you got to realize you got the coil voltage, you have the contact current, and the number of contacts. Okay. Let's talk about that. Here's a little bit of animation on the isolation. You can see here, I have a battery powering up a relay right here to turn on 110 volts. You surely wouldn't want to mix the two. So when you turn it on, you can see the contact switch on that thing. You see my load switches too. Okay, so you'll see this load switching, and we call this a changeover contact. Okay, so it's got a normally open and a normally closed, and it changes over from one source to the next. Okay. Control relay, signal isolation, different control signals, different control voltages, and multiple configurations. Look at this here at the bottom. This is some terminology you need to understand when you're dealing with relays. Let's start off with the first one. That's a single pole, single throw. You see the difference in the single pole double throw, okay? So the poles are definitely the commons, and the throws are the set of contacts. So you can see here at the bottom, I have a double pole. I have two different commons. And then I have a double throw, so it can go either direction. That's some terminology that it's good to be aware of. Okay. And some of our control components you can just see are push buttons. A lot of people will buy these push buttons in different types. This is our modular series. Most of the companies out there all have this modular series, where you'll have an operator on the front. You'll have some contact blocks. We do it right here. Operator. You'll have a holder that kind of holds those things together against the operator. Then you'll have a set of contacts on the block. If it's illuminated, you'll have a lamp block in the middle. There's also another one called our monoblock, and these are nice, all one piece units. You got the LED and you got the contacts all right there built into one. Now that's a pilot light. Okay. Yeah. Now here's our selector switches. Here we go. Selector switches work kind of like the push button, but you got a little more control. And there's usually a little truth table down here at the bottom I'm showing. When I turn that switch in position 1, or position A or position B, which set of contacts get closed? Which ones get opened or actuated, I should say. Three positions, you can kind of see how that works. The middle position will always be on for hours. Some common notation, though, I like to show everybody at the bottom here is, well, that first one is a maintain, just says ABC. And then look at the one at the right of that. That's a spring return from the A side, from the left side. All right. And here you are in the 3-pole switch. You got an ABC there. And they're all maintained. And these are key removal. Usually when you see a dot above it, that's going to be where I can take the key out of it. So if it's one of those key switches, that's the location I can take the key out. Here's the one in the middle on the right. It's a spring return from the right. And I can take the key out only in the middle position. That said, I think you kind of get the gist of that. What else we got here? Pilot lights. Okay. Here's the different ones. The modular one, as I'm showing here, you have your lens, your operator, that lock nut, the holder, and then you'll have a lamp module that'll fit up inside there. Or you can have these monoblock down here that's all built into one. Okay. You don't have to put all that together. Typically, OEMs like these monoblock series where everything's all built into one. Otherwise, most people will get these modular ones and then they can mix and match whatever contacts they want to put on the back of it, whatever color they want to use. They can minimize the inventory. Go ahead.
Blake, are your illuminated products all LED now, or do we still use some incandescent?
All of ours are LED. We don't have any more incandescent.
Very nice. Okay.
Makes it kind of tricky because you're trying to cross this sometimes and they'll have a transformer and then they'll have this generic bulb. Well, we do all that at once. We don't go from one voltage to another. You got to buy that LED for the voltage you're using. Really, it makes it a lot easier. And of course, the LEDs last longer. They're more brilliant. No heat, not near the heat anyway.
Okay. And second question.
Yeah.
The 22 millimeter standard versus the American, which was that?
Yeah.
30.
Yeah, you're right.
How do you deal with that?
Pretty much the standard, like nowadays, there's the 22 millimeter. It's nice. You can get the same kind of operators. And what's interesting, if you took that and you have a push button. Here's a little test you do. You take a 22 millimeter push button and a 30 millimeter push button. You put a nickel right in the middle of it. You're going to find out that button area is the same. We do have a 30 millimeter adapters that go with this stuff. And we've really made it easy by anytime you have a part number, just add D30 at the end of it, and you'll automatically get the correct adapter that goes with it.
But the button itself, as you say, will look the same size.
Yeah. The button itself is just all this other housing around it is why it's 30 millimeter. That was kind of a legacy thing. That was what we did years ago. But as time went on, they went smaller. They realized the European market they really liked what was happening with the 22 millimeter because they were reducing the size and the real estate on the panel door.
Excellent. Okay, thank you.
Uh-huh. Potentiometers, same game. A lot of people ask for these things, and all it is again a potentiometer that is in a 22 millimeter housing. Used to you get these things, you got to solder those leads on, but ours have screw terminals on it, so all you got to do is land your wire in there and screw it down tight. We have some buzzers also, and when you're crossing buzzers or you're looking at buzzers, you got to look at the dB rating. How many decibels will that thing produce? You can imagine if you have to seal this thing up for an IP69, you're going to dampen some of that sound. So that's why we show also an 80 dB, because we have one that's got a little more washdown capability. Okay. Limit switches, same kind of game. You're playing with the contacts. But when people ask me to cross a limit switch, a lot of times they'll just send me this body. They won't send me that actuator head at the top. That's the only way we sell them is all in one piece. So I know some of the other companies out there can sell these actuators and then they'll sell the body separate. We sell them all in one piece. So when they give me those things for a cross, you're going to have to give me the whole thing. They're very detailed. You can get into different angles of movement. Where does the switch trigger? Is it a snap action or is it a smooth action? One of them is a little more accurate than the other. So a lot of detail in these things. So you just got to be aware of it. Applications, you can see all the different doors and limit switches and food processing machines and gates. Maybe when like here the conveyor, when the box gets to the end of a conveyor, it indicates it to stop. Okay. Foot switches, that's another control device out there, and these have different things to look for. I think this little breakdown I found on the slide is really nice. These are just our plastic ones, but you can do a single pedal, you can do a double pedal, you can do them covered, not covered. You have them with a safety lever. You have them that'll latch on a double tap. And then of course the contacts. You're still going to be looking for how many normally open and normally closed, maintain or momentary. Okay. Transformers. This is one I like to talk about just before I talk about my power supplies, which you can tell us on the next slide. What's the difference between a power supply and a transformer? Well, a transformer is basically, the way I like to put it, it's a gear reducer for electrons. So if I have a 10-to-1 transformer, yeah, I could put 100 volts in one side and get 10 volts out the other. And yes, if I flip it, I can put 100 volts on the low side and have to step up to 1,000 volts. Yeah, it'll step it up just like that. Now you're not going to get the power. The formula was always power in equals power out minus some heat loss. But that's all a transformer is. It's just a reducer. It's just to reduce it. You reduce it up, you reduce it down. Works both ways. And usually you're sizing those things by volt amps. Volts times amps is usually power, right, without any reactance. But that's how you size those things. Now let's look at the power supplies. Power supplies got a little more involved in it. This is where we're taking AC voltage and turning it into DC voltage. And they used to do it real simple with just a bridge rectifier and some capacitors and maybe a voltage regulator on the output. But nowadays they modulate that thing. They take that waveform, they modulate it. They all modulate it up around 100 kilohertz. Then they go back to a computerized microprocessor in the power supply and turn it back into 24 volts DC without any ripple. So even if you had the old linear style power supplies, you had a little bit of a ripple in there. It wasn't a true 24 volts DC. You could actually see some ripple in there. But now their ripple was like 0.1 volt peak to peak. But now with these new switching power supplies, you're like 0.01 peak to peak. So you got a lot cleaner through power supply. And also a lot of power supplies, since they have such a capacitors in them, you get this, as you power it down, it still holds the power ride through, I think they call it. Switching power supplies have got other electronics built in it. I think they call it a crowbar circuit. So you can basically touch the two wires together and it'll turn itself off, take the wires apart and reuse the thing. I used to demonstrate that with a little 2.5 amp power supply. You don't want to do that with a 20 amp power supply. You get a big arc that scares everybody. But you can see that these come in single phase power supplies, two phase power supplies. They also come in three phase power supplies. So a lot of times on the single phase power supplies, you might build your control circuit with 110 volts and then decide you need 24 volts to run some DC stuff. Or you do a step down that way, or you can just go directly from a three phase right into 24 volts DC. Okay. And then we also mentioned the redundancy modules. So if I create a 24 volts DC and it's the only thing I got is a 20 amp power supply, but I really need 40 amps out there. Well, I can use these redundancy modules and put two of them and get the 40 amps with two 20s. Basically, all it is a back-to-back diode. So if one power supply goes out or the ripple, that little ripple that I mentioned earlier is out of sync, it keeps them from fighting, the regulators from fighting each other. So you can put this little back-to-back diode between two different power supplies and get your 40 amps without harming, without overheating the devices. Nice technique. Okay. Then we'll talk a little bit about the plant layout and distributions through the plant. You've got your service entrance coming in from the power company, and you asked me earlier about molded case breakers. Well, these up here around the switchgear, we're probably not going to have those. We're going to have these more towards the industrial control panel over here by the motor control centers. Those are where we're going to be putting those are going to be the molded case circuit breakers we're talking about. But let's talk about that a little bit. So you got some terminology you got to understand when you're doing the disconnects and feeders like this. You'll have your main distribution, then you'll have what they call a feeder, okay? And when you're dealing with disconnects and circuit breakers, a feeder is basically, and the easiest way to put it is from one switch to another switch, okay? And a branch is going to be a switch to a load. So if you got some kind of a switch that you want to just turn a motor off and on, that's going to be a branch. If you got something in feeding your control panel that's going to feed another switch, that's our feeders. Okay. They'll come in different flavors, fused, non-fused. You'll have some enclosed ones. Okay. And again, in the big picture, you can kind of see where these reside over here on the far right. Okay, molded case circuit breakers, and these things will have this 65 Ka circuit. And everybody says, well, why can't you just use a regular circuit breaker? Well, the molded case breakers will have these higher short circuit ratings. Okay, so if you get it dead short, it blows up. You've got some ratings on there to keep an eye on to guide you accordingly. Okay, here's some more towards the bottom of the spectrum. Okay. Here you go. Here's a branch circuit. Here's some branch circuits. But you can see if I get on top of all these red lines, these are going to be feeder circuits. Just to give you an idea. Now we're talking about miniature circuit breakers. You have the two different ratings. You have the 1077 and UL 489. 489 is going to be that feeder circuit from a switch to a switch. The 1077 will be a switch to a device. And usually you can tell this by looking at the fins. See, I got that red arrow at the top. Those 489 breakers will typically have those fins on it. And basically, I think we just wanted to see some spacing between the two terminals. So you put them fins on there and we're all good. Unfortunately, you can't just come back and add the fins. You got to buy it that way. On our product, yeah, they don't want people, I guess, buying these things and pulling the fins off, trying to fool the inspector. Disconnects. Now we're dealing with UL 98 or UL 508. And be aware, when you see this UL 60947, standard. That was a harmonization done, I think, around 2018, 2019 with the UL 508. So it's all UL good. Okay. So the UL 508 is a switch to the device, and the UL 98 is from a switch to a switch. Okay, and you can kind of see in the 489, it's got those fins on it again. You see them big black fins there, all of them. Now you'll see here I have in the bottom left, you got a UL 1008. That's for changeover switches. Okay, so if you're coming in from one power source or another, you're trying to come out to feed a distribution, and then we have this UL 1008. Okay. Your safety devices, you can imagine all the different places you can put a safety device on these things. We have safety relays. And one of the things I look for when I'm crossing these safety relays and I'm trying to help somebody get one, look at how many safety devices. Can you see that in the upper left corner? You got K1, K2, K3. This has got 3 contactors in series for safety. And I've got a way to control that with our safety relay. Sometimes you'll see that in 2s or 1. Okay. We also have a programmable safety relay. You know, I'm like, God, why would you ever need a programmable safety relay? Well, there are some conditions in these robot cells or inside of a machine that there's certain conditions. You want to make sure the guy actually, when he opened that gate, that he's in a safe condition. You want to make sure that he can't close that gate behind him. You want to make sure he goes through a certain sequence that he gets out of the gate area, closes the gate, walks over here, touches something 3 times, and then hits the start button. A little bit facetious there, but you can understand some of this requires some programming, unique situations. We have what we call a programmable relay. There's a few of them out on the market. The gate, some of these gate sensors, that RFID gate, safety gate sensor, those are kind of nice because you really only have to run a wire to one side of these things, and there's little coated magnets in that other side. You got hinged operating switches. Now they're all, you notice these are red and they all have a safety certification on them. I can't just put any limit switch on there and expect it to meet safety standards. I had a job one time where a lot of the safety gates were just limit switches. Like, all right, let's get them off and at least get them on there where they're a safety limit switch, and that way we're covered a little bit. You can see the key operating switches with and without a solenoid. Solenoids are handy because you want to make sure that it's turned off, and sometimes you'll have to energize this solenoid to make sure the rest of the machine's turned off. You can't just say, well, he can go over and open that gate and kill it. Well, no, we don't want to stop the machine by opening a gate. So that's the intent there. Cable pulls. Some of us have seen these cable pulls all the way around a conveyor system. So anybody along that line can just pull that cable and get a safety stop. Okay. There's some other safety devices, some e-stops, palm buttons. And again, these aren't just palm buttons. These are actually safety rated palm buttons. There's a standard for that. 2-hand starts. What is that all about, Mike? Well, so if I reach over and put one hand on one of those black buttons and get to talking to somebody, and then I reach over and hit the other button, it won't start. It's got a little timer in there. You have to hit both of those buttons in a certain amount of time. Otherwise, somebody may take one of those buttons down, or they may wedge something in there, so they only have to hit one button. That's why they do a 2-hand start on them. Focused beam light, single beam light curtain. You can do a single beam with a little beam in the middle, or you can do the whole light curtain, which covers an opening. Okay, that's it. So we can summarize now. Motor control circuits, we covered it. Some control components, from our power distribution, and our safety stuff. Anybody got any questions? Good. Am I still there?
Blake, thank you very much.
Okay.
I learned. I'm the most important thing I got out of this was the fact that our 22 millimeter product with the 30 millimeter adapter is basically the same as a 30 millimeter button. I didn't realize that the button sizes were all the same, and it was just the adapter and the mounting hole.
Well, a lot of there are some true. I mean, if you go to our flat series, it's a true 30 millimeter. There's no adapter. There's a lot of them out there that are 30 millimeter, but 22 millimeter has just taken over the industry so well that we want to accommodate the legacy stuff, but we have to do it with an adapter. We're not going to make a whole separate button for it unless you do that
Right.
flat. You know.
Well, I think the trend is overwhelmingly toward 22 millimeter, but we still got, we still got some holdouts here. It tends to be just an American thing, I would imagine, the 30 millimeter holdouts.
Yeah. Yeah, that's the only place I've seen it. It's some of the older American stuff. You strip out a panel and you clean it out. You still got these 30 millimeter holes in it. So,
Right.
you're going to have to go back with a 30 millimeter to fill the hole.
Okay. Well, good. Blake, thank you very much again. Thanks for coming to us from Texas.
I hope I left time for your VFD class.
Well, no. You're fine. In 2 weeks, there's a VFD class, and I will present the presentation on some of the new standards associated with the short circuit protection for VFD. You mentioned the UL standards, UL 508, and the new 5-letter one that starts with a 6. I can never remember that one.
Yeah.
But those are dictating changes in the world of VFDs as well, and I'll hold a class on that in 2 weeks. Next week, Chris Keller's up, and he's going to be talking about some advanced cable technology that we use, especially with regards to specific applications like VFDs. In the closing minutes, I wanted to mention something that has come up quite a bit for some reason in the last 3 or 4 weeks, where people are coming to me and asking me about soft starts and where soft starts should be used. So in the last few minutes, I'm just going to make a very short explanation. There's a misconception in the marketplace that soft starts are used for inrush current control. And that's not what they were originally intended for, and not how they're designed. In some cases, the SCR-based voltage ramping device that is a soft start can have an effect on inrush current. But soft starts were originally designed to limit the output torque during starting of an AC induction motor to protect belts and gear teeth, etc. It's a mechanical advantage, and it does pretty good with that. The problem with a voltage controlling device like an SCR-based soft start is that its current control as a result of the fact that it can only control voltage is very load dependent. And therefore, you can never really predict very well how much current's going to rush through when you start the motor. Now, we all know that when you use the contactor, the motor's going to pull, we used to say 600 amps inrush current when you just bang the contactor home, no soft start. But these days, with these new low slip, high efficiency motors that are meeting the new federal standards, the inrush currents that I've been seeing are closer to 900 or 1,000%. So you have a 10 horsepower motor, 460 volt, its full load amps are going to be around 12, 13 amps. And you can see over 1,000 amps of inrush current on that. 100 amps of inrush current on that thing. That's just made the problem worse. Putting soft starts in place to limit that inrush current, it will help, but it's not predictable. So if you're using soft starts to limit your inrush current to keep your peak power down, to eliminate, say, peak power penalties from the power company on your overall usage of power on your facility, the soft start is sometimes going to work and sometimes not. When the load is, say, a pump, a centrifugal fan, something like that, the soft start can do a decent job of limiting inrush current. But when the motor starts into a load and that soft start ramps up, that current is not going to be limited very well. And you will pull a good percentage of the inrush current that motor would pull across the line. So just bear that in mind. A soft start is a very good mechanical shock limiting device, but it is an unpredictable inrush current limiting device.
Glad you
And
brought
if you
that
really
up.
want,
That was good.
yeah,
I had to have that explanation myself.
and if you really want to do, if you really are have to have good control of the inrush current on an AC induction motor during start, whether it's a centrifugal load, whether it's unloaded, whether it's fully loaded, you've almost got to go to a variable frequency drive. That's where you get good control. You're going to pay more? Absolutely. You know, on the lower horsepowers, the drives are maybe 2 times the cost of the VFD, and we're talking hundreds of dollars, you know, maybe into the low thousands. But I can certainly understand the conundrum when you're into a 2, 3, 400 horsepower situation, and the soft start is a lot less than the VFD at 300 horsepower. Problem is, you know, if you pick up a screwdriver to do the job of a hammer, you're not going to do the job well. You got to have the right tool. So again, soft starts are a great tool for limiting mechanical shock to the load during starting of the motor. They are not a predictable tool in limiting inrush current. And with that, it's 7:57. It's time to go to work. We'll see you guys next week. Blake, thanks again. It's always good to see you.
Thank you.
All right, take care now. Have a great
Thanks,
week.
Ferris. Take care.
Thank you, guys.
Bye now.
Thank you all.